All right, here we go. Rotational motion. So I would encourage you to pay attention. I would encourage you not to have conversations during this time, because I really want to make sure this makes sense to you. When we're talking about something rotating, it has to have a couple of things in order for it to be an approachable system for us to look at. The first thing that we are going to require of all of our rotational motion systems is that it is what they call a rigid body. So the opposite of rigid might be, I don't know, what do you want to call it? Fluid, or what'd you say? Placid, yeah, like it's, oh yeah. It's moving, right? Does that make sense? Can you imagine something that as you move it or as you rotate it changes shape? What would be an example of something like that? What'd you say?
A rubber band with a weight on it.
A rubber band with a weight on it? So as you're rotating it or moving it? Sure. What else did you say?
A football.
A football. Does that change shape?
No, it doesn't.
Well, it probably would a little bit.
A little bit, but so little that we're going to call it negligible. Jack, do you have something to share?
Nathan's example?
What did Nathan say?
It's a golf ball.
Is that a rigid body? A golf ball? Pretty close. Yeah. Again, so this is how you can take this, guys. You can take this in two different ways. Number one, you could say nothing is a rigid body. Okay? Because it's really true. If I rotate anything, does it make sense that there's going to be a centripetal force acting on that object that's rotating about a circle or rotating about a point? Yes, we talked that through, okay? In uniform circular motion. And if it's not uniform, then there's going to be even another force, right, that's causing it to speed up or slow down. So you can have this thing that's rotating and there's forces acting on it, and as a result, absolutely there would be a little bit of stretch that happens. But in those things that we're calling rigid bodies, we're saying that that motion is very, very small. So if we throw a football, does it change shape? It would, but not by much. Not by much. For our purposes, it's not going to. What would, as it's rotating, actually physically change shape? Like an object. Can you think of anything? A ball of, that's what I was thinking of. A ball of Play-Doh. What did you say? A water balloon. Absolutely. So something that's got fluid in it, right? That's going to change its orientation or its, what do I want to say? Location. Okay? These things that we're going to talk about, and this is not to say that everything is a rigid body, but we're going to approximate them to it, okay? It's some sort of, so instead of the opposite of this would be a point particle, it's an extended object okay, whose size and shape does not change as it moves. Okay? So it's not going, or that doesn't happen in these kind of situations. Okay? When we talk about the motion of this rigid body, and I kind of alluded to this earlier, but I just want to make sure that you have this out here. Okay? There are three types of motion that we can talk about. Okay? The first is translational. That's what we've been talking about for the last however many weeks we've been together. Okay? So that would be if I take the frog and I throw him. You going to catch him?
Oh, am I catching?
I hope so.
Okay.
Translational motion, right? He's just moving in a straight line, so the object is moving. Now, there's another option. Rotational motion. Make him rotate.
Make him rotate?
Yeah.
So just that is that what we're talking about? I'm very confused.
Yeah, I guess. I mean, that's okay. Anybody think of another way that we can make him rotate a little bit more interestingly than by...
Probably not.
Put him on a throw him and put a little spin on.
What was that?
Grab like a throw him up, whack him on
Okay.
the bottom.
Okay, now,
Backflip.
what you all are discussing, like, so something like
Yeah.
that, okay? Was there rotational motion in that? Sure. Was that purely rotational though?
No.
No, it wasn't purely rotational. There was some translational as well. So the third kind, we'll go back to rotational in a second. The third kind is what they call just combination. So that's going to be translational and rotational. Purely rotational motion is when you have an object that is rotating about some fixed axis. Okay? So rotating about some fixed axis. And that's what we're going to focus on for much of this chapter. Okay? The first section, 12.1 in your book, is basically, it basically says, it actually says in bold, go back to chapter 4 and reread it. So I'm going to tell you, go back to chapter 4 and reread it. That was the chapter where we talked about rotational kinematics. So I just want to remind you of that rotational kinematic stuff so that you can go back and read it intelligently, okay? Because those pieces are really important and they're going to come back to... Gabe, do you need something? What's wrong?
No, there's
It'll be okay. It's not going anywhere. It'll be okay. You'll be all right. I promise. Do you remember when we talked about rotational kinematics? Yes, yes, I do. We had 3 variables that we defined. 3 things that helped us to describe rotational motion. What were they? Angular velocity, and that was marked with the letter omega. No. Like, seriously? No, it's not. So don't say it. Thanks. What else you got?
angular acceleration, which was alpha.
Yep. So we got acceleration, we got velocity, we also need position or displacement, which is marked with theta. And then remember we went through and derived, or restated, I guess, all of the kinematics equations in terms of angular variables. So I just want you to remember that. Go back through, make sure you remember that. And then did we also talk about sign conventions? I can't remember if we did that last time or not when we were talking about this. Did we talk about positive and negative?
No.
Yeah.
I think we did. I just want to make sure that we define it so we don't forget, okay? So the sign conventions are that if something moves counterclockwise, so that would be in this direction, we call that positive rotation, right? And something that moves clockwise, this direction, is negative. And again, just a reminder that that is totally arbitrary. Somebody had to decide, and that's what they picked, okay? But it's just like when we take the frog and we hold him up here and we say that down is going to be negative. We just had to pick it. You can do everything and call this the positive direction, and that's fine. It's just not going to match anybody else's stuff. Does that make sense? Okay.
Never mind.
Okay. You can do it. You just, it's not recommended.
Conventional.
It's just not conventional, yes. It's unconventional. All right. So there's another concept that we have to talk about when we're talking about rotation that kind of helps to put everything together, and that is the concept of center of mass. Have you heard the term center of mass before? Yes. Where have you heard of it? Like, what is it? You have to compute it in calculus. Okay, let's talk about more practical applications.
Yeah, like if you could bounce with a pencil at that exact point would be the center of mass. That's what we talked about in like 8th grade.
In 8th grade. Okay, so how many things have a center of mass?
Everything.
Everything has a center of mass, right? The center of mass is the place, it's the balance point, okay?
Yes.
Of a rigid body or a system. Okay? So if you're thinking about building an object or balancing something, in order to balance an object, the basic statement, and we'll talk about this in much more depth later, but the basic idea is that the center of mass has to be over the base of support, right? If you have something like, if I put this out here like this, is it going to balance? Is it going to fall?
No.
It is going to balance. It isn't going to fall. Look, because it's not. But does that mean that I can put this out anywhere? No. If I put this out like this, is it going to fall? Sure. Why?
Because the force of the table is no longer equal to the force of the floor. Table pushing
Because your mass is
There's
off
not
the table.
much table.
Right. So there's this like that, you know what I'm saying? Like if I push up right there, then life is good. But if I now, so like no, but so there we go. There are papers under there. It's just not quite as exciting. But like you can find where that center of mass is, right? Because you can find that balance point. So it's not super hard to do that if you have a nice uniform object. It's much less easy if you have a less uniform object. Does that kind of seem to make sense to you? So what's that?
They still make you do it in calculus.
Yeah, I'm going to make you do it a little bit here too. We're going to go through it. I don't.
Non-uniform objects too.
Yeah. Yeah. Like a water. No, not a water balloon.
Is that
Not a water balloon, but we're talking about like some sort of object that is not of uniform density, right? Because if you have something that's not of uniform density, then it's not just going to be right in the middle. That's what I'm talking about. Okay. So I want to talk through this a little bit with you, and then I want to do a little lab to kind of help fit this together, and then we'll do the derivation. And I don't know how much you do in calculus, so I'll just kind of we'll throw it around and see where we're at. So the other thing to know besides just balancing things, because balancing is fun, but that's not really rotational motion. Okay. The other thing that's nice to know is that the center of mass is the point about which hi. An object will rotate if it's unrestrained. Okay. I have seen this demo a bunch of times, and I was going to have you do it, but then I was like, it's going to be too hard to figure out. So I found a video of it that's pretty lovely, and Gabe's going to go turn the lights off after he's done writing down what he's going to write. And I'm going to show you this just to kind of get your head in the game for this. Hopefully this will work.
both lights?
Yes, please. So this is from MAT's demo department. So he's got this object, looks like it would look like a tennis racket or something like that. I don't know. This is just a mass on a stick, it looks like. They're gonna do it. Hold on just a second. Yeah. So they're just throwing stuff. Yay, look at that fun thing. And it's kind of hard to imagine. That disc is not uniform. So now they're gonna do what Nathan wanted them to do. So that's the that racket, right? Kind of hard to catch because it's hard to predict, but the center of mass has been marked, and you can see the center of mass, and it really does just move in a parabola. And so they're going to throw that with some good spin on it. But it still works, even if the throw is bad. I would agree. The throw is not great.
Well, they're from MIT, yeah.
Yeah.
I don't think that.
It's true. It's true. They're not the best at.
They're not the best athletes in the world.
Yeah, but they do show a center of mass, so that's nice. Yeah, that's what I just heard. They're pretty awesome. Yeah, I think they had 1 loss this season.
Harvard had 0 losses.
Yeah.
That's what Steph was so excited about.
Why do we care? I don't know. All right.
Jackson, like,
Yes, please. So, the idea here, my friends,
Sports Center went to Harvard Junior.
is that center of mass, when you have combination motion, will just follow parabolic motion. So when we are doing anything with projectile motion, really the thing that we're looking at is the center of mass. Even if you have an object that's rotating, as long as you know where the center of mass is, you're good to go. Then you just use projectile stuff, life is happy. But you have to find that center of mass. So that's what we're going to talk about now. Okay? So in your book, the way that it kind of derives, since this is the first time I've gone through all of this, don't have a brilliant other way to do it. So I'm just going to kind of walk you through the way that the book does it because I think it's kind of nice. Okay? To derive the definition of center of mass. So really what they do is they throw it at you and then they kind of unpack it and get to the calculus. Does that sound okay? So we're going to do the same thing. I'm going to tell you that to find the center of mass of an object, you really just need to know the coordinates. But if you have like a 2-dimensional object, right? If you have the third dimension is relatively uniform, then finding your x and y coordinates will tell you that center of mass. The x coordinate, I don't know what my computer's doing. It's like I want to be on break still. The x coordinate of the center of mass is equal to 1 over the total mass of the object times the sum of all of the little masses. We're going to break it up into a bunch of little masses. And each of those little masses is located at a certain point.
What's the upper limit?
We're just adding them all up.
Oh.
So we're just summing from 1 to n, however many there are. Is that okay? So we could write that out then if you wanted to be really fun about it. You could write this out as mi xi, let's actually do 1 and 2 and 3. That'll be better. So m1 x1 plus m2 x2 plus dot 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 m and xn, we'll say there are n of them, divided by m1 plus m2 plus m3, etc.
to make it even more fun.
We are going to in just a minute. Yes. Did you just hear him? Okay, this is what just happened in Gabe's little head noise making experience. I just have to share this. We can make it into integrals and make it even more fun. I said, we are going to. Oh. Like, really? You were so excited and then, like, come on. Does it make sense we could say the exact same thing in the y? Just change this to a y and change these all to y's, and it's all the same statement. So we're going to find the x coordinate, we're going to find the y coordinate. So this is saying for each little piece and its location, we can find the center of mass if we know those little bits.
This looks disturbingly like what we're doing in calculus right now.
Sweet. I don't know what you're doing in calculus right now.
Trying to define area.
Oh, okay. It's the same kind of idea. Absolutely.
Like, how do you determine like what you want to break it up into?
Yes. We're going to make it an integral, so it won't matter. Hold on just a little bit. Okay. So, here's the thing. This is kind of this is the generalized statement, but let's make it a little simpler to start with. So if we're going to make it a little simpler to start with, let's say, so a simple example. For a simpler example, let's have an object with n particles. Does that sound okay? And each of those n particles has a mass m. So that means that m1 and m2 and m3 and m4 are all the same. Is that okay? So we're talking about a uniform mass. Okay? Like, I don't know, maybe a meter stick, assuming that the wood is all nice and uniform. It's pretty darn close. Okay. So I'm going to break this up into 100 particles. Each of them has the same mass. Life is okay. If I do that, then finding the location of the center of mass is going to be a whole lot easier. Would you agree? What's it going to look like then? Can you write down an expression for the x and y coordinates? Have a little conversation at your table. What would it look like?
Okay, you did 100.
N. I'm doing n of them.
Okay. Yeah, that's true.
Well, if they all have the same gas, you can factor out M at
Yeah.
the top. And since you have a bunch of them, just add it up on top. You can factor that into equal. So you can cancel it out.
Yeah.
dx
So it just
over the
equals
whole
X coordinates are good.
Right, so you have to add up all the x coordinates. You take the average of all the x coordinates.
Yeah, yeah, okay.
And then you're done, right? It's not hard. This should not be like a blow my mind moment. I'm not saying that it was super fast, but I'm saying it's not a blow my mind moment. Logan, what'd you guys figure out back there?
Right? The top becomes n times n times n.
It's just the x.
Oh, and over and over again.
It's what'd you say?
All the masses cancel, so it's just the x deal. x1 plus x2 plus blah, 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 blah. All those.
Okay, so just that?
Yeah.
Is it just, I mean, do you just add them all up? So if this one's at 1 and this one's at 2 and this one's at 3 and a 4 and a 5, I'm just going to add them all up? Where do you think the center of mass of this is going to be?
At the 50.
At the 50, right? Yeah, more or less. I need to move my finger a little bit. There we go. Okay, at the 50. So I'm not just going to add them up. What am I going to do?
Divide by n.
Divide by n, and that's where this is coming from. All of these masses are the same.
Yeah.
Yeah, each with mass m.
Uh,
So I need to divide by n. And does it make sense that we could do the same thing for the other part too? Okay, so that kind of is a nice, simple example. I want to do another example. This one is not quite, well, it might be okay. We'll see.
Wait, hold on.
Yeah.
I get like why it should be that, but like why that if you do the
You
algebra,
plug in the algebra, you have n times n in the denominator.
yeah, don't you have that at the
Then
top too?
m times the sum of the.
Yeah, you can factor it out at the top.
Yeah, you factor m out, but you still have the n in the denominator.
There's no n in the numerator.
Yeah, there's no n.
But you have n m's in the numerator.
Yeah, but when you factor it out.
Yeah, but when you factor, you
m
don't add
times
them
the
together.
sum.
Oh, never mind.
Yeah. Are we okay?
Yeah.
Okay. You don't need to beat yourself up over it. It's Monday morning. You've eaten. You're like in this like pumpkin pie like zone. Oh right, pumpkin. It's like cheesecake.
Yeah, no.
Pumpkin cheesecake. All right. Example number 2. A little less simple, but close. Here's the situation. Example number 2. We've got a 500 gram ball and a 2 kilogram ball. On either end of a, for our purposes, massless, let's just keep it simpler for now, 50 centimeter long rod. Okay? I would like you to find the center of mass. Give it a shot.
Are you
Find the location of the center of mass.
So we should see like the distance from
Yeah.
a given center.
Yes. Yes.
I can rewrite them.
Okay, so what are we fighting about? Talk to me. It's 10. So as an AP Physics reader, if you just said 10, I would say wrong.
Literally writes down, it's just 10.
And then I would say 0, right? On a 1 to 5 scale, that's a 0. Try again. 10 what? Or 10, I mean like,
Zero's not on a 1 to 5 scale.
I know, that's my point. It's like so bad that I wouldn't even,
So
yeah.
bad it's not. Centimeters. It's so
10,
bad
okay.
you have to change the scale.
Gentlemen. 10 what?
Centimeters.
10 centimeters. 10 centimeters what?
Away
From
the
the 2
kilogram ball.
on the.
What? From the 2 kilogram ball.
Is that okay?
No. Doesn't it say in the direction of the other ball?
Well, it may no, but it's not a vector. I mean, it's on. I think it's fair to assume that it's on the bar.
It's floating somewhere.
Just assume it's on the ball. You don't need to say on that.
Right.
Right.
Okay.
That's what I'm talking about.
All right. Let me tell you the plan, friends. What's that?
She has a 7-day forecast.
Oh, yeah, because Casino really liked it too.
Okay, we got to stay focused. Thanks. A uniform rod, we're going to divide it into little tiny masses. You guys are awesome.
Thank you.
Because it's a uniform rod, we know that dm over m is going to be equal to dx over the length of the rod L. We only know this because all of the pieces are going to have the same, like a little piece of mass to the whole mass is the same as the little distance to the whole distance because it's uniform. Okay?
Is that a big M over the little one?
No.
It's the same m. Sorry. It's the same m. So we can say dm, d little m. Ah. Mm. If I make noises, it makes it better. Big M over L, dx. So then I'm going to plug this thing in for dm. And then I've got a nice expression that is more consistent, let's say, to find the center of mass. 1 over m times, I'm going to write this as m over L, that's the same m, that's a big M, times the integral of 1 over x dx. Is that an okay statement? So again, I could pull that m, or not again, but I can pull that m over L out because that doesn't have anything to do with my x here.
Is this the integral of 1 over x?
No. No, not 1 over x. I'm sorry. I don't know why I wanted 1 over x. My bad. You guys got to talk to me. I was just excited about fractions. I don't know why. I can cancel the m's. So now the total mass doesn't matter, right? If it's uniform, the total mass doesn't matter. The only thing that matters is the length. I wanted the 1 over L. That's where my 1 over was coming from. I apologize for that. And really, we can integrate that from bound to bound because we're talking about from one side of the rod to the other. So that's like from 0 to L. And if you integrate x, that's going to give you 1/2 x squared. So you've got 1 over L times x squared over 2, evaluated from 0 to L. And that gives you the location of the center of mass as 1/2 L, which shouldn't surprise you.
Whoa, that's amazing. It blows my mind.
You're sarcasm.
I thought it would be.
I am not taking any bit of sarcasm. There was no sarcasm in that comment. And now it's time for Gabe to leave. Goodbye. And the rest of you.